Okay, that sort of brings us to a new topic, the relationship between strings and number systems. We just saw how every character is actually encrypted as an ASCII character. We also know that every decimal number that we work with is actually encoded in the computer as a binary number. So we're going to have a little fun with this right now. Here's a few examples. We have the value 415. What would that look like in binary notation in base 2? In other words, we're counting using only zeros and ones. Well, here it is. 11001111 base 2. Now, I want you to notice the subscript here. We have a 2, we have an 8, we have a 10, we have a 16. Formally, when we represent numbers, we should show the base of the number that we're depicting. However, since by default the normal number system we work with is base 10, or the decimal number system, all right, 415 in decimal notation is itself 415 base 10. As long as we're working in the default base, we normally don't put the 10 subscript. All right, but when we start working with other bases, we always include the subscript just so that there's no confusion. I mean, obviously, without the base 2 here, this could be a decimal number. This could also be a decimal number. This could be, and is, a decimal number. This one you might look at a little funny, all right, base 16. We would not mistake this for being a decimal number. It is, in fact, a hexadecimal number. It is base 16. So if you are in a context where numbers are being represented in several bases, remember, always use the subscript to show what base you're referring to. All right. Now, in case you weren't aware of this, the digits that are used in each number system are counted from 0 to n-1, where n is the number of the system's base. For instance, in base 2, binary, we only have the numbers 0 to 1 because 2 minus 1 is 1. So we go from 0 up to 1. And then we have to cycle back. If we are using base 8, octal, there the numbers run from 0 to 8 minus 1, or 7. So we can only have the highest value in base 8 is, or the highest digit, I shouldn't say the highest value, the highest digit is 7, right? And if you have, let's say you're counting 0, 1, 2, 3, 4, 5, 6, 7, and you want to go one more, well, 8 in base 8 is 1, 0. Just as in the decimal notation, we have digits 0 to 10 minus 1, or 9. So we have 10 available digits, 0 through 9. When we get up to 9 base 10 and we add 1, we have to place a 0 in the units place and then shift over a position. And the 1 in the tens place means that I have 110. So that's where we get 1, 0 in base 10. In hexadecimal, we actually have digits 0 through 9, A through F, because we have to represent 10, 11, 12, 13, 14, and 15 as a single digit in base 16. Otherwise, we'd screw up the idea that it's a positional number system. You know, you can't shove 2 digits in one position. So that's a quick example for these different number systems. So by way of explanation, in positional notation, a digit has a positional value. And that the value is determined by raising the base, whatever the base of the number system is, to the power specified by the position. Base raised to position. So how do we read the value 210 in base 10? Well, what is it? You've got 3 positions: the units place, the tens place, and the hundreds. Where do we get units, tens, and hundreds? Well, 1 is 10 to the 0. 10 raised to the 0 is 1. 10 raised to the 1 is 10. And 10 raised to the 2 is 100. So therefore, we have 210. And that's how we figure it out. Here we look at how we derive 415's value in base 10. 415 is equal to 4 times 10 to the power of 2. Remember, the index starts at 0. 0, 1, 2. Right, so 4 times 10 to the 2 plus 1 times 10 to the 1. 0, 1. 1 times 10 to the 1 plus 5 times 10 to the 0. 10 to the 0, or 1. So 4 times 100 plus 1 times 10 plus 5 times 1. That gives us 400 plus 10 plus 5, or 415. Well, it doesn't matter what base you're working with. They all work the same way. If this were a base 2 number, and it were something like 110, then we would have 1 times 2 to the 2. 1 times 2 to the 1. 0 times 2 to the 0. And we could add up the values and find out what value we were working with. So let's look at this idea of converting binary to decimal. Each digit or bit in a binary number has a positional value that's therefore a power of 2. All right? And sometimes you may hear a binary number referred to as a string of bits or a bit string. So this could be referred to as a bit string. Now, to determine the integer quantity that a string of bits represents, this is how we would work it out. Again, just so that there's no confusion, the final one here represents the position of 2 to the power of 0, or 1. This next position, 2 to the 1, or 2. Next, 2 to the 2, or 4. Next, 2 to the 3, or 8. Next, 2 to the 4, or 16. Next, 2 to the 5, or 32. And then finally, 2 to the 6, or 64. So let's work this out. Since this is 2 to the 6, we simply take 1, since there's a 1 in this position, 1 times 2 to the 6, plus 1 times 2 to the 5. Now we have 2 zeros next. That's just 0 times 2 to the 4. You don't even have to do it. It's not going to come out to anything. Plus 0 times 2 to the 3. Right? These obviously come out to 0. Plus, now we have another 1. 1 times 2 to the 2. Plus 1 times 2 to the 1. Plus 1 times 2 to the 0. Work all these out. 2 to the 6 is 64. 2 to the 5 is 32. 2 to the 4 is 16. 2 to the 3 is 8. 2 to the 2 is 4. 2 to the 1 is 2. 2 to the 0 is 1. All right, so now that we've plugged in the actual values, you can just go and figure this out. 1 times 64 is 64, plus 1 times 32 is 32. 0 times 16, 0, ignore it. 0 times 8, 0, ignore it. 1 times 4 is 4, So we're going to add in the 4. 1 times 2 is 2, so we're going to add a 2. And then 1 times 1 is 1. You add all these up, and you have the decimal value 103. Clever. Since the test embedded in the for loop is true, we're going to go on to line 5. Execute line 5, execute line 6. After 6, we don't go to line 7. We're in a loop. So we go back up to line 4, and we will execute 4, 5, 6. 4, 5, 6. However many times given the length of our B string. When we finally get to the end of our B string, and we finish processing the last bit of the B string, don't forget that you go back up to the header of the loop first. So we don't exit out the bottom. We don't go 4, 5, 6, 7, ever. We go 4, 5, 6, back to 4, and then line 7. All right, so that's just a quick example of what a thread of execution problem looks like, and we'll be working through some of those. Now I'm going to leave this one because it's rather lengthy. I'm going to leave this version that converts decimal back to binary for you to go through. All right. In fact, I don't know why this is convert binary to decimal. It's the opposite. Many times you're given a decimal number and you want to find its binary value. So this would show you how to do that. Right. And it just reflects the mathematical algorithm for doing it. It's in loads of textbooks. Your textbook explains it somewhat. So I'm not going to go through this in detail, but you should definitely walk through this code and practice doing it. Sorry about that. Okay, so we're laying out the bit positions. At the rightmost bit, we would call position 0 because it is represented by 2 raised to the power of 0. This is 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3, 2 raised to the power of 4, 2 raised to the power of 5, and 2 raised to the power of 6. So then you can lay it out. You've got 0, 1, 2, 3, 4, 5, 6. And this works especially good on graph paper because you can line everything up quite nicely. Now we put the values underneath, right? Obviously 2 to the 0 is 1, 2 to the 1 is 2, 4, 8, 16, 32, 64. Notice you're doubling each time. It's base 2. Everything doubles for each position. Now, you don't have to put 0 through 6 up here, but it will prevent you from forgetting one. It will prevent you from, leaving one of these out. Now, you list the bit string to convert. All right, here's a bit string. 1, 0, 1, 1, 0, 1, 1. All right. Now, every time there's a 1, you note the value. If there's a 1, it really means a 64 in base 10. Wherever there's a 0, you don't care because 0 times anything is 0, so you're not going to wind up with a value here. Here I have a 1 in the 16's position, so I have to list the 16. Here I have a 1 in the 8's position. I have to list an 8. 0, don't care. A 1 in the 2's position. That should be a 2. I don't know why it's a 1. And a 1 in the 1's position. Okay, so this needs to be a 2. Okay, so I see I'm going to need to edit the slide. That should be a 2. So 64 plus 16 plus 8 plus 2 plus 1, if we add those all up, we will in fact get a total of 91 base 10. So that's an easy way to go from a bit string to a decimal number. Now, if you're going in the other direction, it doesn't have to be so hard either. Again, you could do sort of the opposite. lay out your powers of 2. You could go up to, say, 7, right? And if you go up to 7, the value of 2 to the 7 is 128. If your original decimal value is 91, obviously there are no 91s in 128. However, there is a 64. So you would take your decimal number, subtract the highest power of 2 that you can from it, in this case 64, and put a 1 in that position. All right? So you would take 91 minus 64, which would give you, my arithmetic's not so good, 27. All right? And now that you've got 27, you would say, what's the highest power of 2 that can be represented by 27? Well, 32 is too big. All right? So I'd have to go to 16. There is a 16 in 27. So I would then put a 1 down for 16. All right, 27 minus 16 should give me 11. All right, so now I'd go and see what's the highest power left that can be represented by 11. And of course I have 8. There's an 8 in 11, so I put down a 1 that represents that 8. And that leaves 3 left over. So I go now and look for the highest power of 2 that can be represented by 3. 4 is too big, so anywhere it's too big, you just slide down a 0. I go to 2. All right, well, obviously there's a 2 and 3. So I put down a 1. 3 minus 2 leaves a remainder of 1. I see if there's a power of 2 left that can be represented by that. And indeed, we've got 2 to the 0 is 1. So there's our 1. 1 minus 1 is 0. So we now have gone from decimal 91 to our bit string 10111011. Now, for certain values, there are some quick ways to compute the values, either going from decimal to binary or binary to decimal. Obviously, if a number is a power of 2, that's pretty easy. It's going to be a 1 followed by a bunch of zeros, depending on the power. Here we have 2 to the 3, or 8. All right, 8 is 2 to the 3, so we've got the power 0, 1, 2. Here's the 3. Put a 1 in that position. Here we have 2 to the 2 is 4. So we start with the power of 2 to the 0 is 0. 2 to the 1, 0. 2 to the 2, that's the 4. So you put a 1 in that position. Okay, and we can do that again with 2. 2 is a power of 2 to the 1. So again, we start with the 0 position. We put a 0 there. And then the next position over would represent the 2 to the 1. So we'd have to put a 1 in that position to represent it. Finally, we get 2 to the 0 is 1. And that is simply a 1 in that 2 to the 0 position. 0, of course, is equally easy to represent. It's just a single 0. Or sometimes you see these bit strings in patterns of 3s or 4s. It's absolutely legitimate when you're talking about this, like you're writing down values or whatever, say on a test, to say that 0 is 0, 0, 0, 0. 4 zeros in a row if you're grouping them in groups of 4, or sometimes you see them in groups of 3. You'll see why in the next couple of slides. But it does make it a little easier. It's kind of like, instead of using commas as we do with decimal numbers, we use space with binary numbers. So the groupings help the eye to see just how many actual digits are there. Now, just as it's easy to go from a power of 2 decimal to a power of 2 binary, or a power of 2 binary to a power of 2 decimal, right? I guess we kind of went from decimal to binary. Let's just quickly go in the other direction. I see binary number 1. It's in the 0th position, so that represents 2 to the 0, which is 1. There you have your decimal number. Same thing here. I have a 1 followed by 0. This works in every case where a 1 is followed by 0. So you just have a single 1. So I count the positions. Position 0, position 1. This is 2 to the 1 is 2. There's my decimal number. Let's go back to the 4. Count my positions. 0, 1, 2. 2 to the 2 is 4. There's my decimal number. Right? And then finally, let's go to this one. I count my positions. 0, 1, 2, 3. 2 to the 3 is 8. There's my decimal number. Well, it's just as easy to get the number that's 1 less than a power of 2. 1 less than a power of 2 is always all ones. All right, so here, let's look at 7. It can be easily shown that when I count up from 7, all right, if I were to do arithmetic here, 1 plus 1 would give me 1, 0. So I have to put down the 0, carry the 1. 1 plus 1 is 0, is 1, 0. Put down the 0, carry the 1. Again, 1 plus 1 plus 1 is 0. Put down the 0, carry the 1, and here it is. Okay, so when we add 1, we're to a value that is already all ones, we actually kind of flip over to the next position. It's like going from 9 to 10, or 99 to 100, or 999 to 1,000 in base 10, right? This is what happens in base 2. So here we have the 8, 1 less 7. Just think of what is 8 and have 3 digits and not the leading value. So here we wanted to pick a 3. That's 1 less than 4. Right? So 4 is 1, 0, 0. Therefore 3 must be 1, 1. And here we've got a 2. 1 less than 2 is 1. This is 1, 0. So we eliminate a position, and every position that's left is 1. All right, so notice that 1 less is always all ones. Here we have 7, 3, and 1. Okay, so a quick way, here's an example, a quick way to compute the decimal value of the number 1, 1, 1, 1, 1 base 2. So this is 0, 1, 2, 3, 4. Go one more power, 2 to the 5. All right? 2 to the 5 minus 1. 2 to the 5 is 32, minus 1 is 31. And that's 31 base 10. So that's a quick way. If you're given something like that, don't panic, and don't waste time adding everything up. Right? Because what is this? It's 16 plus 8 plus 4 plus 2 plus 1. Right? You could add all that up and you get 31. But an easier way is just say, I'm going to add 1 to get me to the next power of 2. 2 to the 5 is 32 minus 1, 31. There's my answer. All right, I talked about the grouping. We have base 2, base 8, and base 16 are actually all very much related. And in fact, it's pretty easy to convert from octal to binary, from binary to octal, or from binary to hexadecimal, hexadecimal to binary. It's got to do with the way the binary numbers are grouped. So to convert from octal to binary, by the way, just a note, you need to have some idea of this, but I'm not going to give you a problem like this in a test. To convert from octal to binary, start by assuming that each digit in the octal number represents 3 digits in the corresponding binary number. So you start out with an octal number, in this case 437. 4 is 100 in binary. 3 is 011 in binary, and 7 is 111 in binary. So put it all together and you've got your binary version of the octal number. So it's quite easy to go from octal to binary. Now, to go from binary to octal, again, you want to group your binary number into groups of 3. 100, well, 100 is 4. 011 is 3. 111 is 7. So then you easily put that together into octal 437. Okay, same thing with hexadecimal. It's actually quite easy to convert from hex to binary or binary to hex. In this case, we use groupings of 4 instead of groupings of 3. So we replace each hex digit with the corresponding 4-bit binary number. So in this case, for instance, we have hexadecimal 4, which in a group of 4, remember you have to do this in groups of 4. 100 is 4, but remember, to add the group, you have to have a leading 0. So 0100 is hexadecimal 4. Here we have hexadecimal 3, which would be 11, but put the 2 leading zeros in front of it to get a group of 4. 0011 is hexadecimal 3 in that position. And then we have hexadecimal F. Right, F would be in decimal 15, right? And so remember we said the shortcut, all right? So we have here 0, 1, 2, 3, 2 to the 4th is 16, minus 1 is 15, all ones. 1, 1, 1, 1 is binary 15. Here we have hexadecimal 15. Now to convert from binary to hex, all right, again, you group them in 4. You figure out, okay, 0100 is 4. There you have it. 0011 is 3. There you have it. And as we said, all 4 ones is 15. And 15 is depicted in hexadecimal as the letter F.